Good afternoon, guys. This is the video lecture for chapter 8. Chapter 8 is about the Earth, the living planet, the Earth, the planet where we live, and the first terrestrial planet that we are going to speak about. And the next chapter, chapter 9, we'll be talking about the cratered worlds, which are the Moon and Mercury. Okay. And then the last chapter before the exam number 2 will be the terrestrial planets, Venus and Mars, which we had already investigated them when we did the laboratory in orbits and the superior inferior conjunctions and the opposition in the case of Mars, opposition and conjunction. Now, this chapter has to do a lot with earth science. So the idea of this chapter is to study the overall structure of the planet, the Earth's atmosphere, the ozone layer, answer a few questions like why the sky is blue, the greenhouse effect, which by the way, there is a video about that and global and climate change in the module, okay, right before this lecture, the Earth's interior, the surface activity, earthquakes, radioactive dating, and a few other aspects of earth science like continental drift. I will be showing you guys the slides, but I want to talk about first of the overall structure of the planet. You should know we call the planet a terrestrial, it's a terrestrial planet obviously because it comes from tierra in Spanish is the earth. So the other 3 terrestrial planets, Mercury, Venus, and Mars, they owe their classification to the planet the Earth. So the main idea of this planet, of our planet, is that we can differentiate it into layers. The layer where we are standing right now is the crust. And it has a thickness between 5 to 50 or 55 kilometers. Now, just for you guys to get an idea, we haven't been able to drill beyond, I believe, 12 kilometers. I believe actually, let's take a look. The most or the deepest drill hole on Earth was only 12 kilometers. There you are. It's called the Kola Super Deep Borehole. All right, that was around May 2008. So we haven't even gotten to the 4th part of the crust. You probably are wondering how or why. Well, we will know about that. We will get the answer by knowing that besides the crust, which is only 5 to 50 or 55 kilometers or kilometers thick, we have the mantle, which we can divide it by upper and lower mantle. We have the molten core, the inner and outer core. The inner core is basically solid, made of iron and nickel, mostly iron. And then you have the outer molten core, which has conductive material spinning really fast. Okay, and that's crucial to understand the reason behind the Earth's magnetic field, right? And then we have we can divide the upper mantle into, we can talk about something like the thin crust, the lithosphere and the xenosphere, all right? But the main parts of the Earth will be the inner core, outer core, the mantle, and the crust. And then you have the hydrosphere, which are the oceans, and the atmosphere, which are the layers of the stratified layers, right? Or is divided into layers. And pretty much we have the troposphere, the stratosphere, ionosphere, and exosphere, right? Okay. The interesting part about the Earth's atmosphere, you can probably argue that there are more layers, for example, between the ionosphere and the stratosphere, there is this layer we call the mesosphere. Now, we live in the troposphere. You have to remember that when you look at the clouds or where the airplanes are flying, that's sort of like the limit between the troposphere and the stratosphere. Now, in the stratosphere, in between the stratosphere and the mesosphere, that's where we have the ozone layer, the production of ozone. All right. Now, what's important about the troposphere? That's where convection happens. Now, what is convection? Convection is a very important physical principle. It's a way of how heat is transferred. Thinking in terms of cycles or currents, right? For example, when there's a fire, you have to crawl because the hot air tends to go up and the cool air tends to go down. It's the principle of how you boil water as well. You have current, so the water is boiling all over the volume, but there is a convection cycle happening inside or in the water, right? Now, what's the ionosphere? That comes from the ionized radiation due to the solar wind, right? Normally, that's where you have the auroras. So you should know that the auroras are produced by the interaction of solar particles, solar wind, with the particles, with the charged particles in the atmosphere. They are excited, and then they produce this light by, as you know from chemistry or also from physics, right? Electron can absorb or emit a photon, and then you have a wavelength emitted. That wavelength can be observed by us as a form of light. Light, because it has a different color. It can be bluish, it can be purple, right? The colors that we observe are part of the electromagnetic spectrum, right? The visible spectrum that we discuss or we introduce in the chapter of telescopes. Now, let me show you this slide here. So you have the ozone layer in the upper stratosphere, right? Why is it important? Because it absorbs UV radiation that is harmful for us. But we know since the early 90s that there was a hole, as you can see there, in the ozone layer. This hole was being produced by the CFCs, the chlorofluorocarbon molecules that were being sprayed from, well, sprays, like this one here. Well, not anymore, but because they realized that they were harmful, but sprays like this, right? When you spray it, back in the day, they will release CFCs. Nowadays, these devices are made in such a way that they do not spray. It doesn't cause any environmental hazard. It can just be toxic, but no more CFCs. Then we have the, well, here's a convection cycle actually. There. So the convection depends on warming of ground by the sun. You see the cool air comes down, the warm air goes up, right? So this allows us to explain surface heating, okay? And how the surface re-radiates infrared thermal radiation. In the slide that you guys have in your course, there is a few introductory aspects about the Earth. And then you have the Earth energy sources. So I talk about convection and thermal heating of the surface, the Earth atmosphere, and we have here the greenhouse effect. Now, let's take a look at your slides, the ones that are here in the course. Here they give you some data about the Earth, like the average distance from the Earth to the Sun, the orbital period that you should know, 365 days, 24 hours, the axis of the Earth, 23.5 degrees, the escape velocity for a rocket, right, to leave the gravitational field or pull of the Earth, the mass of the Earth, which by the way, there is a lab on that I will probably be uploading how to do it. In case you are interested to determine the mass of the Earth using a simple pendulum. I think it's a very interesting lab. The composition of the atmosphere. Look, when we talk about the atmosphere, we have to remember that most of it is nitrogen, almost 80% of it. The rest, 20-21%, we're talking about oxygen. And then we have other gases. The main one there will be carbon dioxide and then water vapor. Both are very important in terms of greenhouse. Greenhouse gases are water vapor and carbon dioxide. It's interesting, right? Because many of you probably read or hear in the news that carbon dioxide is very harmful, and it is. But you also read that it's very bad for climate change, and it also is true. However, we have to remember that greenhouse is an important and a crucial property or event or physical property, physical fact that we need in order to have life. The greenhouse effect allows us to have the Earth at a temperature that is good enough for life to exist. The best example will be if we look at the moon. You can consider the Earth and the moon to be a system going around the sun. The distance between the Earth and the moon is almost negligible when you compare it to the distance between the Earth and the sun. So how come the temperature on the moon is so extreme, extremely cold, especially, right? If you guys Google it, to be more accurate, we will talk about that when we talk about the moon, but the temperatures in the moon can go between 120 degrees to minus 100, so between 400 and 140 kelvins, or in Fahrenheit. Look at that range of temperatures. On Earth, in a normal day of summer, we can have a temperature of what? 90s, 95, 100s. In winter can be what? 10s, 20s, maybe minus something, minus 10, minus 20. The Fahrenheit. The range is not extreme between summer and winter. However, for the moon, it's extreme. The reason is because the moon doesn't have an atmosphere, doesn't have a greenhouse effect. So what is the greenhouse effect? The greenhouse effect is what you are seeing here and what you have in the video. Is the fact that light of the sun, some of it goes through the atmosphere, some of it goes through the clouds and goes towards the Earth. It gets reflected back, and then we have surface heating due to the light of the sun hitting the ground. But then we have re-radiation of thermal energy, infrared energy away from the ground. How does the Earth trap that thermal energy? By the greenhouse effect due to the greenhouse gases. CO2, CO, water vapor, as you can see there. Methane as well. All right. Now, we don't want an over-exaggerated greenhouse effect. An over-exaggerated greenhouse effect can produce things like what happens in Venus, where it also has a very dense atmosphere, but very toxic, mostly carbon dioxide and a lot of heavy acid rain due to the intense greenhouse effect, where none of the light or almost none of the radiation from the sun can escape, which is why Venus is the hottest planet in the solar system, even though it's not the closest planet to the sun, right? So the Earth and the moon, they have a huge difference in terms of surface temperatures. And that's because of the absence of the atmosphere in the moon. Now don't get confused. There is no air in the moon, but there is gravity. Very weak, but there is gravity. All right. Why is the sky blue? Because of Rayleigh scattering, right? When the light of the sun is going through the atmosphere, the part that is scattered away from it as the light is entering towards the Earth is the blue portion, the blue part of the spectra, not the red. Now, obviously in the sunset, you can see in summer, the sunset is normally reddish, orangish. That's because of two reasons. One of them is because of the position of the sun. So the sun is very high the whole morning and afternoon, but then during sunset, it's also getting lower and lower towards the horizon. The distance to come, the distance traveled by the ray of the sun is longer. Not as much, but it's longer. Plus, all the remaining red light that wasn't scattered is still there. And they end up overcoming the blue portion in sunset. Let's see what else do you have here. Earth's energy sources, solar energy, the main one, but you also have the motion of the atmosphere, Earth's internal heat, tectonic plates, reshaping of the surface, and then life is due to the solar energy. Convection, here it is, as an example there. And here you have another slide of the Earth's greenhouse effect. Don't forget to go into modules, and please, I want you guys to watch this video about the greenhouse effect. Hopefully it's still available. Yeah. All right, so there is a nice explanation for that. I will see if I can put another video about continental drift, okay, which is also very important for this chapter, because once we talk about the atmosphere, the composition of the Earth, the ozone layer, the greenhouse effect, convection, and the energy sources for our planet, now we can start discussing about the composition of the planet. We talk about the core, the inner and outer core. But what happens in the mantle? The mantle is rock. It's not the same type of rock that we have in the crust, because the rock in the mantle is subject of a lot of pressure and temperature. That's the reason why we cannot drill a hole that goes beyond 12 kilometers. As you go deeper and deeper, the pressure is intense, right? Remember that we right now are withstanding an atmospheric pressure of 1 atmosphere, which is around 1.01 times 10 to the 5 pascals. It's a lot, but we can live on it, right? All right. As you go deeper, you know, when you go deeper inside a pool, you start getting, you start getting hurt or a little bit of pain in your ears. That's because of the water pressure. Sorry, that's because of the pressure. The pressure due to water plus the atmospheric pressure. So that's the same that happens when you want to go within the planet, right? Plus the temperature also increases. Okay, so the best way to explain the Earth's interior is by looking at it as if it was an onion with different layers. The core is there, the outer core, the mantle is the largest part. Actually, sorry, the core it is. Look, I can show you the better slide here I have there. See, you see that? Look at the units. So the radius of the Earth is around 6,400 kilometers. More than half of it is the core, the outer core, right? The inner core is just 1,300. And look at the crust. It's almost nothing, right? So it's very important that you guys remember that. Look, if you were on campus, I will be asking you to draw this in an exam, or maybe to explain, right, what it is, each of those layers. What happens on each? For example, in the mantle, you have the tectonic plates, and you also have the P waves and S waves that we're going to talk about in a second. They are the ones that we use to map and to know these numbers with certain accuracy and precision, right? The S waves and P waves are the ones that we call seismic waves. And the ones that we feel here on the crust are surface waves. So P waves and S waves, they do travel across the planet. Now, since you guys are not on campus, unfortunately, I cannot ask you things like that, right? I do understand that it's complicated for some of you to draw, but expect questions where I will be asking you to either discuss or analyze. Okay? Now look, P waves and S waves. You should know by now. If you don't know, that's okay. But in physics, we have two types of waves, transverse and longitudinal. Transverse waves are light, sound, the wave that you make in a rope, where the direction of propagation is perpendicular to the vibration itself, right? It's going up and down, but the wave is moving, in your case, in your perspective, horizontally, from left to right, but the oscillations are up and down, perpendicular. That's transfer. Longitudinal, which are P waves, are where the direction of propagation is parallel to the direction of vibration. Okay, so for example, a spring. A spring is a longitudinal wave. And the thing about that is that that's the key difference between P waves and S waves. That's how we get the studies of earthquakes. That's how we study earthquakes, because earthquakes are due to the collision, right? Or the movement of tectonic plates. Now, there are a whole bunch of things that we can study if we just do earth science. There are convergent, divergent boundaries, right? There are transverse boundaries, translate, and there are also the physics behind rifts, magma coming and then producing volcanoes. That's all earth science. And that's very interesting, by the way. I hope that you guys did that in school. If you didn't, this is sort of a crash course on that. All right. But what you need to know is this. No, before we get into that, it's going to there, this slide. So P waves and S waves, they both go through solids, but it's only P waves that go, the one that can go through liquids, as you can see in the graph there. So we use the reflection during the earthquake, as it says on the slide, to deduce the interior structure of the earth. Okay. P waves and S waves also have a difference in speed. And they also have a difference with the surface waves that we can actually study here on the surface. So we can pinpoint different locations and then try to study and get things like the shadow zone, all right? Or areas where P waves are actually transversing or traveling, sorry, and where S waves are not. A good example would be the outer core, right? Molten. S waves do not travel through there. S waves will only travel through the mantle. So there you are. When we have an earthquake, there is an epicenter and a hypocenter. The epicenter is the location where the earthquake happened, projected on the surface of the earth, on the crust, normally on the ocean, right? But there is a hypocenter where actually the plates collided, or there was an interaction between the tectonic plates. That's the hypocenter. So we can triangulate where the epicenter was by studying the arrival of P waves and S waves. Normally the difference on time. Okay, normally we use triangulation because we need points on the surface and 2 points in the interior. And that's how we can triangulate this. So that's more seismology, right? P waves, those are called compression waves. You see how it moved there? And then you have S waves, and that's how they move. There it is, right? Like a wave, like a sine wave. Okay. I like to show this as well. How the density and the temperature change as you go from the mantle to the core. So the temperature obviously is the greatest in the core, over 4,000 to 5,000 kelvins. Just to give you guys an idea, the temperature on the surface of the sun is approximately 5,800 to 6,000 kelvins. Now, I know that some of you may not be used with kelvins. What is Kelvin? It's a scientific unit for temperature. Around 1,000 and beyond, so millions, 10,000s, millions, billions. You can say that a Kelvin, so for example, you can say that 6,000 kelvins is approximately 6,000 degrees. You know why? Because the difference is of 273. It makes more sense, or there is more difference if you talk about 100 kelvins. So 100 kelvins is minus 173 Celsius. It's huge. But as you go into the range of temperatures for the surface of the sun, it's almost negligible. All right, but still, kelvins is the temperature that we use for astronomy to get the temperatures of the core of the sun, of the surface of the sun, or stars in general, and also for planets. But also take a look at the density. So density is the rate between mass and volume. So clearly, even though the core is the largest part of the Earth, more than half, more than 50% of the Earth is basically the core, right? 3,500 kilometers of radius. It is also the more dense, and that's because of the composition of the core, which is mostly metals. And metals, as you know from the previous chapter, are the ones who have the highest density, and then it's rock, right? Which is why Earth, Mars, Venus, and Mercury, especially Mercury and the Earth, have the highest density, and why the Jovian planets have the lowest density, because they are mostly made of gas. Now, when you look at a map of the Earth, you probably have been shown this. The continents fit as a puzzle. That was one of the evidences for Alfred Wegener to think that the continents were not or are not static. What happens is that there is something called continental drift. So it's like the continents were one a whole, okay? And then due to the continental drift that we can also investigate it due to seafloor spreading, right? We know that the continents were once joined together approximately 250 million years ago into what we know as Pangaea, the super or the mega continent, right? We know that there were other ones before that, so the continents have been attaching and detaching due to the continental drift. But when he proposed that idea, Alfred Wegener was not taken seriously because there was not enough evidence, according to the people who were doing the peer reviews. So what is the evidence then that we have nowadays? The main evidence, I would say, is seafloor spreading, paleomagnetism, and fossil records. For example, the Mesosaurus. The dinosaurs were extincted 65 million years ago, but they lived for a long time. We're talking about around 300-400 million years. I'm not a paleontologist, so I don't know exactly, but I know they lived for a long time. So 250, 220 million years ago, there were dinosaurs. So an example would be the Mesosaurus. So we have found fossils in extremes of the planet when we know that they were not able to, if the continents were like they are now, there is no way, for example, for an animal to go from one place to another. Okay, so we know that the whole continents at some point they had to be together. So these Mesosaurus or other reptiles had to be able to travel from one place to another. So that was one. Continental drift was also, as I say, seafloor spreading, and paleomagnetism is just the idea or the fact, sorry, that some metals on the seafloor that we have found, for example, gold or zinc, right? They record the previous magnetic orientation of the Earth, right? And this allows us to further study that the fact that the Earth has been dynamic, the plates, the seafloor, the polarity of the magnetic field itself as well has changed, right? So Now we have evidences for that, but back then there was not. Look at this slide. He proposed that in 1915. So there is the evidence there. And obviously, look how long it took for it to be accepted after the Second World War. It's incredible, right? Okay, so you have to remember that the entire area is covered by the surface by crustal plates, which can move independently. And then, the earth boundaries, the plate boundaries, sorry guys. That's when earthquakes and volcanoes can be produced. You have the convergent, divergent, and the transverse. Let me show you that here. If you look at that, you can see that we have the oceanic plate and the continental plate, and you have a trench, like the Mariana Trench. The lithosphere is right below it. It's the upper mantle, per se. So when you have a convergent boundary, the oceanic plate tends to go within. That's because of the difference of density, okay, between the continental and the oceanic plate. And then, depending on how it's produced, you can get a volcano, right? So that is a nice example for a convergent plate. Let's take a look at divergent. For a divergent plate boundary, you normally can have this division, and you can have also a small rift. Something like this, a rift valley. Now, depending on the type of rift, you can produce also volcanoes there, because magma goes up all the way, and it can be escaped in a volcano in what we know as lava. All right. Now, as this slide was saying, right, we can have earthquakes also in plate boundaries, depending on the interactions. Okay, so these things are very important in the study of earth science and our planet itself. Now, I skipped this in these slides. Let me see. So we talk about this. The mechanism of tectonic plates. So remember, the energy for this to happen is due to convection currents that are happening on the upper mantle, below the hydrosphere, below the oceans. All right. Rift Valley there in Kenya. And there it is. That's an example there of a convergent plate between the Indian plate and the Eurasian plate, which produce what? The Himalayas. All right, guys, I think that is what I want you guys to study. There is also this slide about the magnetic field, which I already explained. But in order for you guys to understand this better, I will share you guys a video of how auroras and the northern lights are produced. But that slide is basically what you need to know. Solar wind colliding with the Earth's magnetic field, elongating it, breaking it at some point, and then the particles coming and converging on the poles, on the north and the south pole. All right. So, and that's also how the Van Allen belts are produced, by the way. All right. Okay. So let's leave it in there. I think this video was long enough, and I hope that you guys enjoy this lecture and the videos I will share. The quiz for this chapter will be at the end of the weekend, and then towards the end of the weekend, I will be uploading chapter 9 video lecture on the moon and Mercury. Now, if you have access to an earth science book, please check it out. I think it's very important that you guys know the physics of like the greenhouse effect, the ozone layer, the atmosphere layers, the composition of the earth, the P waves and S waves, plate boundaries. Maybe that's going a little bit and beyond, but it's important regardless. I will be sharing the other set of slides as well. And I hope that you guys have a good afternoon. See you guys next time.